Hey y'all, welcome back. On tonight's homework, we are going to be going through some problems that require some understanding of some different theorems that we went over in class, specifically the fundamental theorem of calculus, the mean value theorem and its friend Rolle's theorem, the intermediate value theorem, and the extreme value theorem. So the first page of this homework is going to cover those theorems, and then because we're towards the end of the year here and the AP test is coming up pretty soon, the second page is just going to be some sort of random practice getting ready for that test. So number one says, what value of c in the open interval of 0 to 4 satisfies the mean value theorem for the function f of x equals 3x squared minus 4x plus 5. So the mean value theorem basically says that if you have an interval and your function is continuous, which this one is, all polynomial functions are going to be continuous, from 0 to 4, the value of the function at 0 and at 4, and we'll find out exactly what it is, but just to kind of give you an idea of what we're looking for in this problem, the mean value theorem says that there will be some point in between 0 and 4 on the curve, let's say it's up here, that has the same, that the slope of the tangent line at that point will be the same as the slope in between the 2 points of the two endpoints. So if your curve is doing something like this, there's going to be some c value where that happens. Now, I'm just kind of making up this curve. This is not exactly what this graph is going to look like. As we investigate a little further, we'll be able to refine this sketch, but that's kind of the idea. And so we're looking for that c value where that happens. So we do have this function, f of x equals 3x squared minus 4x plus 5. So let's go ahead and find out where the function is at those endpoints. So when x is 0, the value of the function is going to be 3 times 0 squared, which is going to be 0, minus 4 times 0, so we get another 0, plus 5 is 5. So when x is 0, the y value here is 5. Now when x is 4, we have 3 times 4 squared. 4 squared is 16, times 3 is going to be 48, minus 4 times 4 plus 5. So we've got 48 minus 16 plus 5. 48 minus 16 is going to be 32, plus 5 is 37. Okay, so when x is 2, y is 37. This is obviously not going to be drawn to scale, but it's going to be something like this. And we're not going to investigate much further as far as like what this graph looks like, but what the mean value theorem states is that somewhere between 0 and 4, the instantaneous rate of change of the function will be equal to the slope of this secant line. So maybe the function's doing something like this. I don't know. Again, that's not really important here. You could investigate further by just simply plotting more points, but that's not really necessary. But we're looking for the point where we've got that exact same slope. So where the slope of the tangent line, which is the instantaneous rate of change, is equal to the slope of the secant line, which is the average rate of change on that interval. So let's find the average rate of change between 0 and 4, and we can just use the slope formula, our classic y2 minus y1 equals x2 minus x1 to find that. So the slope of the secant line is going to be f of 4 minus f of 0 over 4 minus 0. So it'll be 37 minus 5 over 4. 37 minus 5 is going to be 32. And 32 divided by 4 is 8. So what we want to find is the c value where the slope is 8. Okay. Now to find that, we're going to have to find an equation for the slope, which is going to be the derivative of f. So let's find f prime. F prime using the power rule is going to be 6x minus 4. And so we're interested in where that tangent line, where the slope of the tangent line is equal to the slope of the secant line. So we'll let 6x minus 4 equal 8. add 4 to both sides to get 6x equals 12. And so dividing both sides by 6 is going to give us 2. So what this is saying is that when x is 2, okay, so our c value we know is 2, the slope of that curve at x equals 2 is going to be the same as the slope of the secant line that passes through the points on the ends of that interval. So our answer is x equals 2. Now, the curve might be actually concave up versus concave down. It might be doing something like this, but even still, we're going to have that slope. I'm not investigating any further. I guess we could see, this is an upward-facing parabola. It opens up because the a value is positive. So most likely, it's actually going to be doing something like this. So this might be a little bit more accurate of a representation of what's happening here. Either way, the idea is the same. We're trying to find the x value that has the same instantaneous rate of change as the average rate of change on that interval. Number 2 says if p is a continuous function on the closed interval 1 to 3 with some value k in between p of 1 and p of 3. So basically this is saying there's some number in between the y values. This is kind of leaning towards an intermediate value theorem problem. And c is the closed interval 1 to 3, then which of the following statements must be true? So yeah, the intermediate value theorem, or the IVT, basically says that if you have a continuous function on an interval, that if you find the y values like p of 1 and p of 3, which we don't know which one's bigger, but we'll just say p of 3 is bigger just for argument's sake, then there's going to be some number that we're going to hit in between. That's going to be the k. Okay? So if k is here, p of 3 is here, p of 1 is here, then between 1 and 3 on the x-axis, there's going to be some number, which we'll call c, that hits that y value. Okay, in other words, f of c is going to equal k. So that's what the intermediate value theorem states, and this happens if you have a continuous function. So if it's continuous from 1 to 3, you have to hit that k value at some point because it's in between the value of p of 1 and p of 3. So let's go through our answer choices and see which one makes the most sense here. A says that p of c equals p of 3 plus p of 1 divided by 2. Okay, so half of so c, well, this doesn't have to be true, right? It might be true, but it doesn't have to be true. It doesn't even tell us what c is. So c could be anything. It doesn't have to be halfway in between p of 3 and p of 1. It might be above p of 3, it might be below p of 1. It may just be somewhere in between that interval, but not necessarily equal to the average of those two. Okay, p of c equaling p of 3 minus p of 1, the difference, and then divide by 2, same thing. That's not really what the intermediate value theorem is talking about. C says there is at least one value c such that p of c equals k. And I wrote this as f. I should have wrote it as p. But that is exactly what the intermediate value theorem says. So our answer is going to be C. But just to be sure on these, which of the following statements must be true problems, it's really a good idea to read through all of them, even though if you think you know what the answer is. D says there's only one value where p of c is k. Well, you might have a function that does like something like this, where if k is here, there might be multiple c values that have that k. The intermediate value theorem just says there's at least one time where you're going to hit. So to say that there's only one value, that's not necessarily true. And c doesn't have to be 2 either. It doesn't have to necessarily be halfway between the interval. It could be any number in between the interval. Number 3 says, if f is continuous on the interval -2 to 6, then which of the following must be true? First, that the derivative has to be 0 for some c. Well, we can pretty easily sketch an example, or we'll call counterexample, where that's not the case. So like if I have 2 points from here to here, and it's continuous, I could just draw like a straight line in between there. We don't have a slope of 0 anywhere on there, so it's definitely not going to be 1. 2 says f has a minimum somewhere. Now this has to be true because of the extreme value theorem. And maybe I should have written down, I said IVT in the last one. This is the intermediate value theorem. Did I write it for number 1? It just says mean value theorem in the problem, so I'll just leave it like that. But anyway, the extreme value theorem says that if you have a closed interval and the function is continuous on that open interval, then you will for sure have a maximum and a minimum. Now, if this said f has a minimum somewhere on an open interval, then that would not necessarily be true because you might have a case where, if you have something like this, there's no actual minimum value there because there's not like a lowest point on the graph. But if it's closed, then you absolutely have to have a minimum. So 2 is going to be a good answer here. And then finally, part 3 says that f of c equals 0 for some c. Well, doesn't have to be true. I mean, I already have a sketch up here to where this never crosses through the x-axis, but still satisfies the conditions in the problem. So 3 is not going to be true. The only correct statement here is 2. So our answer is B. 4 says if f is continuous between a and b and differentiable between a and b, exclusive, which of the following could be false? So could be, meaning not necessarily, but is possible to be false. So A says f prime of c equals, so this is the slope of the tangent line. So the tangent slope at c is equal to the secant slope. So this is like the mean value theorem that we have up here, where we tested to see if those are going to be equal. Well, if f is continuous and differentiable, that this is going to be true. The mean value theorem tells us that there is going to be some c value where the tangent line, the instantaneous rate of change, is equal to the average rate of change. So yeah, this is not going to be our answer. B says f prime equals 0 for some c value. Now, that actually could be false, right? Just because we have continuity and differentiability on this interval doesn't necessarily mean that the slope has to be 0. Okay, so no matter how I draw this function like this, maybe it's like this, but we see like on this, like especially if it's like linear, the slope does not necessarily have to be 0. So I'm pretty sure that's going to be our answer. But again, with these kind of problems, you want to double check on the rest of them just to see if they could be false also, and see if there's some flaw in our logic. C says f has a minimum value. Well, that's what the extreme value theorem gives us, is that there for sure will be some minimum value on that closed interval. Again, if it was the open interval, then no, we couldn't necessarily say that. But because it's a closed interval and it's continuous on that closed interval and differentiable in the open interval, that has to be true. So it can't be C. D says f of c exists for all c, such that a c is in between a and c. Well, yeah, because it's continuous, then the function is going to be defined for all values. So this is continuity. It's going to grant us that. Tenuity. So yeah, it can't be D. And finally, E, F has a maximum value. That is going back to the extreme value theorem. Okay, so there has to be a maximum on that closed interval, just like there has to be a minimum on the closed interval. So the only one that has the potential to be false is going to be choice B. Number 5 says find a value C that satisfies the conclusion of the mean value theorem. Okay, so we already talked a little bit about what that mean value theorem is, how it works. So we're going to do this again. It's basically going to be the same kind of problem that we had in the problem 1. So first we're going to find the average rate of change on this interval. Okay, the average rate of change on the interval 2 to 5. Okay, is another way of saying the slope of that secant line. And so what we want is f of 5 minus f of 2 divided by 5 minus 2. So we do need to evaluate f of 5 and f of 2, and I'll go ahead and do that out to the side here. F of 5 is going to be 3 times 5 squared minus 5 times 5 plus 1. So what would that be? 25 times 3 would be 75 minus 25 is 50 plus 1 is 51. And then f of 2 would be 3 times 2 squared minus 5 times 2 plus 1. So let's see, 2 squared is 4, times 3 is 12, minus 10 is 2, plus 1 is 3. Hopefully I did that arithmetic right. So we've got 51 minus 3 over 5 minus 2, which would be 48 divided by 3. And 48 is divisible by 3. 3 goes into 4 one time and goes into 18 6 times. So this is going to equal 16. And so we're looking for the value c where the derivative is equal to 16. So the derivative, so now we're looking at for the instantaneous rate of change. Instantaneous rate of change, we're looking for where that is equal to 16. So first we'll find a formula for the instantaneous rate of change, which is the same as the formula for the slope of the function or the derivative of f of x. So f prime is going to be 6x minus 5. We want to know for what x value is that equal to 16. So we can add 5 to both sides to get 21, and then divide both sides by 6. So we get 21 over 6. I think we can reduce that. Both of these are divisible by 3, so we get 7 halves, and our answer is E. Number 6 says let f be a function with a first derivative defined as 3x squared minus 6 over x squared for positive values of x. It is known that f of 1 is 9 and f of 3 is 11. What value of x in the open interval satisfies the conclusion of the mean value theorem for f on the closed interval 1 to 3? So we have basically the same problem that we had on number 1 and number 5, but in this case they're giving us the derivative and the values for f of 1 and f of 3, which are those endpoints. So let's first find the average rate of change on that interval. So we're going to have f of 3 minus f of 1 over 3 minus 1. Now they gave us these values, 11 and 9. 3 minus 1 is 2. So you get 2 divided by 2, which is 1. So we want to know, when is that derivative equal to 1? So when is 3x squared minus 6 over x squared equal to 1? Well, if I multiply both sides by x squared, I'm going to get 3x squared minus 6 equals x squared. And then I could subtract an x squared from both sides, leaving me with 2x squared minus 6 equals 0. From here, I'm going to add 6 to both sides, divide both sides by 2, and then take the square root of both sides. So I get plus or minus root 3. But this is only going to be valid for when x is greater than 0. So we're going to disregard the negative there. And so we just get x is equal to positive root 3. And our answer is B. Number 7 says let f be a function that's differentiable on the open interval. If f of 2 is negative 5, f of 5 is 5, and f of 9 is negative 5. Which of the following must be true? Now, before we really dig into this, I think it might be helpful to sketch out a picture just so that we can more clearly see what's going on here. Okay, f of 2 is going to be negative, so I'm going to actually move that x-axis up a little bit. So here's 2, here's negative 5, got a point here. At 5, it's equal to 5. And at 9, I guess I can squeeze this in a little bit. Let's put 5 here. And then at f of 9, we have negative 5. So it says, which of the following must be true? First of all, f has at least 2 zeros. Now, it says that the function is differentiable from 1 to 10 exclusive, which means that it is going to be continuous. Remember that differentiability implies continuity. If a function is differentiable at a point, it is also continuous at that point, which means that because of the intermediate value theorem, we have to cross over that x-axis actually twice. So f does have at least 2 zeros. It's possible that we have more than 2 zeros, because we could do something like this, cross that x-axis more than just twice, but it does say at least 2 zeros. So we're definitely guaranteed to have at least 2 zeros because we're going to have to cross that x-axis going up and then coming back down. So yeah, definitely letter 1 is going to be a true statement. Number 2 says the graph of f has at least one horizontal tangent. Well, this is going to be Rolle's theorem, which says that, so let me write that down, Rolle's theorem, which is just a specific case of the mean value theorem, which says that if the endpoints of your interval are equal, which they are here, they're both -5, then that means at some point, it might be up here in the middle, or it might be not. We could sketch this in a different way, like maybe it's doing something like this. So not necessarily at x equals 5, but there is going to be some point where you have a horizontal tangent line. And that's, again, due to the mean value theorem, but more specifically Rolle's theorem, which is that special case where both outputs of the endpoints are equal. So 2 is going to be a true statement as well. And so let's look at part 3. We got the intermediate value theorem guaranteeing us that the first one's true, Rolle's theorem, which is an application of the mean value theorem to give us letter 2. And then part 3 says for some c in between 2 and 5, f of c has to equal 3. Well, we can't get from -5 to 5 without passing through 3. So the intermediate value theorem definitely guarantees that that's going to be true too. So all 3 of these statements are true. And our answer is E. Okay. Number 8 says the number c satisfying the mean value theorem for f of x equals sine x on the interval 1 to 1.5 is what? So again, we've got this function, and we'll use Desmos to, actually, let's just go ahead and pull this up. So we've got this function f of x equals sine x. I'm going to go ahead and type that in. And we're really only interested on the interval 1 to 1.5, so I'm going to put a domain restriction on there. Oh, I didn't actually type the function there. Let's see, sine x. There we go. And we'll put that domain restriction of 1 to 1.5 in. So negative, you do that little curly bracket, less than or equal to, x is less than or equal to 1.5. And so this little piece right here is what we're kind of zeroing in on. Okay, so the mean value theorem says that there is going to be some point on here that has the same slope as the slope between these 2 points. So let's first find the slope of the secant line that passes through 1, 0.84 and 1.5, 0.997. Now we don't actually need to round anything here. We're just going to compute f of b minus f of a over b minus a, where these endpoints, the b and the a, will just simply be the endpoints of the interval. So like from 1.5 to 1. Okay, so this right here is the slope of that secant line. And we can actually, since we have that slope, we can create an equation here using point slope form. Y minus y1 equals m times x minus x1. That looks kind of like this: y minus y1. So that would be, let's use any point on here, but I'm just going to use this first point on the interval 1, whatever that is. So my point being 1, f of 1 equals m. So that's the slope here. That's this whole thing times x minus 1. Okay, so can I scroll this separately? I want to kind of scroll I'm not really sure how to do that here. I know I can do it with a pinch to zoom here, but here, we'll just edit it manually. Still not really seeing it very good. Let's go to like 1.1 maybe. Just want to kind of exaggerate that so you can see it a little clearly. Okay, so the slope here is that 0.312, and what we're looking for is a c value where the tangent line has that exact same slope. And so we can come up with that equation of that. So y minus whatever that c value is, okay, we'll figure it out. That's what we're trying to find, equals where we have the exact same slope at x minus c. Okay, so we're trying to figure out like where is that c value? Oh, is it right there? All right, well, let's kind of go through how we'd actually solve it. So normally the way we would solve this is by setting that slope equal to the value of the derivative. So let's write that out by hand. We've got this slope of the secant line, which we said was approximately like 0.312. And we want that to be equal to f prime of c. We're trying to find that c. So let's start with the derivative of f of x. The derivative sign is cosine. And so we want to know, when is cosine of x equal to 0.312? All right, so let's go back to Desmos. We want to know, when is cosine of x equal to 0.312? And actually, I'm going to, instead of like typing this out, I'm just going to say, I'm going to use this value up here and just say y equals that. So I have the exact value. And so those are going to be equal right here. Okay, so at about 1.25345. So the c value is going to be at 1.253 roughly. And so our answer is going to be D, but I also just kind of want to show you that that does work. I'm going to hide these two. And we're going to write an equation of a line using point slope form. So y minus f of 1 equals, and then the slope here should be the same slope. Oh, sorry, f of c, which was that, what was it, 1.253, equals the slope times x minus x1, where x is the 1.253. And so zooming in on here, it's kind of hard to see. You can kind of just see visually how these two lines are parallel. They should have the same slope. And that, you're looking at the tangent line and the secant line. So anyway, I just want to give you like a little visual here so you kind of see what it is we're solving for. So we've got our answer. The answer is choice D. Number 9 says, suppose the function f is continuous between 1 and 2, and that f prime exists on that interval. F of 1 is 3, f of 2 is 0. Let's sketch that out. Like anytime they're giving us a bunch of values, I feel like, and we're just trying to analyze what's happening, it's always a good idea to draw a little picture here. So f of 1 is 3, f of 2 is 0. And so it's saying, which of the following is not necessarily true? A says the mean value theorem applies on f between 1 and 2. And yeah, the mean value theorem is going to apply because f is continuous on that interval, and it's also differentiable on the open interval. So that is definitely true. So this is true, and so that's not our answer because we're looking for the one that is not necessarily true. B says there exists a number c on the closed interval such that the slope is 0. Well, we certainly could find a way to make that happen. Like if I went like this, there'd be a point here where the slope was 0. But it would also be possible to connect those points without the slope being 0, right? Because all we know is that it's continuous and differentiable on that interval. So this one is not necessarily true. That is looking like that's going to be our answer. But let's just go through the rest of these just to verify. So C says there exists a number c on the interval such that the slope is -3. Well, again, we could draw this in such a way where the slope's never going to be -3. Right? Like if I, the slope, if I just make this a linear function like this, going down 3 over 2, the slope would just always be -3 over 2. So it's never going to be -3 in that case. So this is not, oh, wait a minute, hold up. This is not necessarily true. Oh, hold up. Geez, my calculation was a little off there. The rate of change here is down 3 over 1, not over 2. So this does have a slope of negative 3. And so if the secant line it has a slope of negative 3, the mean value theorem states that at somewhere on the curve, you will definitely have a slope of negative 3. So this, is definitely going to be true, and it's true because of the mean value theorem. Definitely not going to be C. D says if k is any number between 0 and 3, so we're looking, I suppose, at the y-axis here. This is probably going to be an intermediate value theorem. Answer choice says there's a number c between 1 and 2 such that f of c is k. And this is always going to be true, like I just said, because of the intermediate value theorem. E says if c is any number such that c is in between 1 and 2, then the limit exists. Yeah, that's because it is differentiable there. So this is going to be true. The fact that it's differentiable on that interval says that the limit will exist really anywhere on that interval. So true because of the differentiability. Okay, so for sure our answer is B. Number 10 says as a fraction, what's the average rate of change? So average rate of change, that's just the slope of the secant line. So the slope of the secant line. Okay, so it's just asking for the slope here from 1 to 4. So 1 to 4, we got 1 comma 2, we got 4 comma 6. We're just looking for the value of f of 4 minus f of 1 over 4 minus 1. Just our classic slope formula. It's going to be 6 minus 2 over 4 minus 1, which is 4 over 3. So that is the average rate of change. Okay, so that wraps it up for problems that involve those theorems that we talked about in class today. Now we're going to change gears a little bit here and just do some mixed AP practice. These problems are just going to be kind of all over the place in terms of content. They're all going to come from problems that were on old AP tests. So hopefully you're able to solve most, if not all of these. But let's go through. If you're here watching the video, then you probably have questions on some of these. So let's get into it. Okay, number 1 here, or 11, it looks like a limit problem because it does say limit, but actually it's a derivative problem in disguise. And that's because of the definition of a derivative. This has taken us way back. But if we ever want to find the derivative of a function, the actual definition of this derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. So in other words, if we are given a problem that kind of looks like this, and kind of the key giveaway here is if you ever see this h approaches 0, I hesitate to say this is always going to be a derivative problem, but on the AP test, this is very common for the h approaches 0 to indicate that, hey, this is probably going to be a derivative problem. But if we want to evaluate this limit, then we're going to find the derivative of f of x, which you can find right here. Okay, so looking at the problem that we have, the limit is h approaches 0 of natural log of x plus h minus natural log of x over h. This whole thing is just going to equal the derivative of the natural log of x. Okay, and we know what the derivative of natural log of x is. This is just going to be 1 over x. And so if x is 2e, 2 times Euler's number, then our answer is going to be choice A. Okay, 1 divided by x, where x is 2e. So this is actually it's kind of an easy problem and a hard problem at the same time. It's easy in that once you recognize what it is you're trying to find, there's really not any arithmetic or algebra or anything like that. You just have to kind of know what you're looking at, and that just takes practice. When you see enough of these limit problems that are set up in this way, you should have this kind of alarm bells going off in your head saying, hey, wait a minute, this is actually a derivative problem. And just know that the derivative is going to come from this function right here. Okay. That's it for number 11. Number 12 says, let f be a function defined below. What is the integral from -1 to 1? So what we want is essentially the area bounded by the curve in the x-axis as a signed area, meaning the area above the curve is positive, below the curve is negative. But since the function is broken down into a piecewise like this, basically what we need to do is break up this integral. We could sketch it out. You don't really need to do this, but just to kind of give you some, a visual on how we're going to set this up, it says that it equals x squared for when x is less than 0. So we got this quadratic for that first piece. Then when x equals 0, it's going to be at -1. And then after 0, it's going to be x. Okay, so if we're going to go from -1 to 1, we need to find the area underneath this curve. So we really just need to split this up. The first section will go from -1 to 0. The second section will go from 0 to 0, which will actually have no area because you're essentially multiplying -1 by 0. And then the third part. Now I'm going to write all three of them out, even though we don't really need that middle part, just so you can kind of see how that works. So from -1 to 0, we're going to integrate x squared. Okay, so that's going to be for that left-hand region here. And then for that middle piece, we know this is going to have an area of 0 because we're just going from 0 to 0. So this is going to have no area. Okay, so there's really no area right here. It's just a one-dimensional line segment, plus the area between 0 and 1. And we'll use x for that. Okay, so now we'll go ahead and use the fundamental theorem of calculus to evaluate each one of these. You can get away with this right-hand one just using area of a triangle formula, and we might actually just go ahead and do that so we don't have to do fundamental theorem twice. But yeah, so let's find the area of that left-hand piece. The antiderivatives of x squared are going to be 1/3 x cubed plus c. We can ignore the plus c's because we know they're going to cancel out. And this is going to be plus 0. Any integral where the upper and lower limits are the same, always going to be 0. And then over here, we're going to kind of shortcut our way through on that right-hand region and just do a triangle formula here. Okay, the base is 1, the height is 1, so it's really 1/2 times 1 times 1. Okay, just a little shortcut there. So you could use the fundamental theorem like we're doing on the left-hand piece, but it's just really not necessary. So on the left-hand piece, if we plug in 0, we're going to get 0. So we have 0 minus, if we plug in -1, we're going to get -1 cubed is -1 times 1/3 is -1/3. We can ignore the plus 0. And then we've got plus 1 times 1 is 1 times 1/2 is 1/2. So we've got 1/3 plus 1/2, which is the same thing as 2/6 plus 3/6. So we get 5/6. Number 13, the table gives us values of the differentiable function f and g and the derivatives at selected values of x. If h is the function defined right here, then what's h prime 1? So basically we need to find the derivative of function h. And it looks like we're going to have to do a little bit of product rule. So it's been a while since we did that, but the derivative of a product is going to be of f times g is f prime g plus fg prime. So let me say that again. F prime times g plus f times g prime. So that's just that first part. And then the derivative of the second part is going to be 2 times g prime. Okay, so if we want h prime of 1, we are going to substitute in 1 for all of these. And so we have f prime of 1 times g of 1 plus f of 1 times g prime of 1 plus 2 times g prime of 1. And so we're going to evaluate each one of these separately using the table. F prime of 1 is going to be -4. So -4 times g of 1, which is -5, plus f of 1, which is 2. I don't see that right here. G prime of 1, which is 3, plus 2 times g prime of 1 again, so 2 times 3. Okay, so now we're just going to simplify this. -4 times negative 5 is 20. 2 times 3 is 6. 2 of those. So 6 and 6 is 12. Plus 20 is going to be 32. Number 14, if f is differentiable function and sine of f of x squared y equals sine of f of x squared, what is the derivative when x is 3? So we're going to have to do some chain rule here. All right, so we've got effectively three functions. We've got our inside function, which is x squared. We've got our middle function, which is f. And then we've got our outside function, which is sine. And so what we're going to do is we are just going to do the chain rule, which says we're going to differentiate the outside function first, leaving everything in between, and then we'll differentiate each function going inwards. So first, we'll start with the derivative of the outside. So bring that over to the pen. dy dx will be the derivative of a sine, which is cosine. So cosine of f of x squared times the derivative of the next inner function, which is going to be this f of x. So f prime of x squared. And then we've got times the derivative of the inside, which is the derivative of x squared, or 2x. Now, if we want to evaluate this when x is 3, we're going to plug in 3 everywhere we see x. So we've got cosine of f of 3 squared, which is f of 9, times f prime of 3 squared, which is 9, times 2 times 3 is 6. So that's our answer. Looking at these answer choices, they're not written exactly the same way, but since multiplication is commutative, you can change the order of these three factors any way that you please. And so we're just really looking for those three factors. And it looks like, I think it's D, but let me double check. We got the 6, got the f prime 9, and we got the cosine of f of 9. So yeah, our answer is D. So we got a triple nested chain rule problem there. Okay, number 15, the limit as x approaches 0. So whenever you do these limit problems, your first instinct should always be to just go ahead and plug it in, see what happens. If I plug in 0, I'm going to get 0 over e to the 0 is 1, minus 0, minus 1. I get a 0 over a 0 scenario. And anytime you have a 0 over a 0 scenario, that means that you're going to have a hole or a removable discontinuity. And so we've got two choices. We can either try to remove the removable discontinuity using factoring. You might look at this and think, oh, wait a minute, I don't really know how to factor that denominator. Maybe it's not factorable. If that doesn't work, if you can't factor it because you've got like e to some power, something weird going on, then you can use something called L'Hopital's rule. Been a while since we talked about L'Hopital's rule, which says that if you get this 0 over 0, or let's say you get 0 over infinity, or infinity over 0, if you get what do I call it? Indeterminate. If you have an indeterminate limit, like a 0 over 0, 0 over infinity, or something like that, then the limit is going to equal the limit of the derivatives. So this limit is going to equal the limit as x approaches 0 of the derivative of the top over the derivative of the bottom. And then we'll try to use substitution one more time. So the derivative of the top is going to be 8x. Derivative of the bottom, we're going to have to use chain rule on the e to the 4x. So you have e to the 4x times the derivative of that, which is just 4, the derivative of the inside function, minus the derivative of 4x is 4, derivative of negative 1 is 0. So yeah, we've got this. Now I'm going to try to plug in 0 again. So we got 0 over 1 times 4 minus 4. So this is still going to be a 0 over 0 scenario. So we're still a little out of luck here, but you can use L'Hopital's rule until it works. So we're going to differentiate again. All right, so let's try that again. The limit is going to equal the limit as x approaches 0. The derivative of 8x is just 8. And then we've got 4 e to the 4x. So 4 times e to the 4x times the derivative of 4x. We got another times 4 here. And then the derivative of minus 4 is just 0. So let's go ahead and try substitution again. Nothing to substitute in the top. So we got 8 over, and then try to substitute 0 in the bottom here. We've got 4 times 1 times 4. 4 times 4 is 16. So we get 8 over 16, which reduces to 1/2. So you might have to use L'Hopital's rule. Like on this problem, we had to use it twice. But this is a rule that you can actually use and abuse, even if it's like a limit problem that you can solve otherwise. Yeah, I might suggest that you just go ahead and use L'Hopital's rule like anytime that you can. I mean, it takes now that we know how to find derivatives, it's sort of a workaround to like saying factor and cancel or do something like that. Now, if the factoring and canceling is easy, you might as well just do it the old-fashioned way. But L'Hopital's rule is super helpful in these scenarios where your limit is indeterminate. All right, moving on to 16, which somehow is 6. It says, which of the following is a solution to the differential equation? So we're basically just trying to solve for y here. But honestly, I think the easiest way to solve this one is just to check each problem and see each answer choice and see which one works. So for example, if y is e to the 2x, that means that y prime is going to be e to the 2x times the derivative of 2x, which is 2. So 2e to the 2x. Okay, if y is 2e to the x, then y prime is going to be 2 times e to the x. If y is sine of 2x, then y prime is going to be the derivative of sine, which is cosine, times the derivative of 2x, which is 2. I'm just going to throw that in the front. And then finally, the derivative of cosine is negative sine. So we're going to have negative sine of 2x times the derivative of 2x, which is 2. And we're going to test each one of these. Oh, wait, it says a y double prime, so we actually have to find the second derivative here. So y double prime for the first one is going to be 2 times e to the 2x times another 2. 2 times 2 is 4, so I'm just going to simplify this here and now. 4e to the 2x. If y prime is 2e to the x, the derivative of that is just going to be 2e to the x. The derivative of 2 cosine 2x, derivative of cosine is negative sine, so we're going to have negative 2 cosine, sine of 2x, and then using the chain rule, we're going to have to multiply by another 2. 2 times 2 is 4. And then finally, the last second derivative is going to be derivative of sine is cosine, so we just have negative 2 cosine of 2x times 2, and negative 2 times 2 is negative 4. Okay, so now what we're going to do is just basically plug in y and y double prime for each one of these and see which one works and which ones don't. So we'll start with A. Okay, y double prime is 4e to the 2x minus 4 times y, which is e to the 2x. Well, that certainly equals 0, so it's looking like our answer is going to be A. But let's double check B, C, and D just to make sure we didn't make an error somewhere. So B, y double prime is 2e to the x, and y is 2e to the x. Oh, wait a minute. That one looks like it works too. Did we make a mistake somewhere? That definitely equals 0. Let's check C. Okay, so with C, we're probably going to have to go back and see where we made a mistake. But C, let's try that one just to rule that one out. Negative 4 sine of 2x minus sine of 2x. That does not equal 0. In fact, that's going to equal negative 5 sine 2x. So we know the answer is definitely not C. And D, we've got negative 4 cosine of 2x minus cosine of 2x. Again, that's not going to be 0. It's kind of the same problem as C. So let's go back and look at A and B and see where we made an error. There's got to be an error on one of these. So let's see. When we differentiated the first one, y prime is going to be e to the 2x times 2. Okay, I'm liking that. And then we got, I think this is right. And let's take a look at B. 2e to the x, derivative of that is 2e to the x. 2e to the x. Oh my goodness. I just realized I didn't multiply by 4 on all of these. Ugh. Okay, hang on. I multiplied 4 on the first. Let's just start. Let's go back. I don't even know if we can eliminate these. We're going to start over because I think I realized where I made a mistake. This is minus 4 times y, not just y. So this one actually is going to be 4 times e to the 2x. So I still think it's going to be a. But let's check the other ones. 4 times 2 e to the x would be 8 e to the 2x. Yeah, that's not going to be 0. Okay, so it's not going to be b. For c, we've got minus 4 times sine of 2x. That looks like close, but that's actually going to be negative 8 sine of 2x, so that's not going to be 0. And with the last one, we've got minus 4 cosine 2x minus 4 times cosine of 2x. This is going to be another case where it's going to be negative 8 cosine of 2x. So this is not going to be 0 either. So yeah, the answer is A. That's very important that, even though you think you got the answer right on the first thing that you try, make sure you check the other answers. So, just in case you did make a mistake, like I made a mistake there. I forgot after that first one to multiply the y by 4 on each one that I tested. So yeah, the answer is going to be A. Number 7 says the function f is continuous from negative 4 to 4. The graph shown below consists of 5 line segments. What is the average value of f on the interval? So the average value. The average value of a function, so the average value, we'll call this f average. We'll just say average value of f is going to equal the integral from a to b of f of x dx divided by the difference or the length of the interval, b minus a. So we're probably going to have to go through each one of these line segments and find the average value. No, we're just going to have to go through on negative 4 to 4 and find, calculate this average value. So we've got the integral from negative 4 to 4 of f of x dx. And so we're going to have to go through and calculate all the areas divided by 4 minus negative 4, which is going to be 8. So let's go through and calculate all these areas. So the area of this first segment, we can see pretty clearly that's going to be 1. It's a half plus a half. So we've got a positive 1 area here. And down here, we've got a triangle that has a base of 1, 2, 3 and a height of 2. 3 times 2 is 6, divided by 2 is 3. So the signed area here, because it's below the x-axis, is going to be negative 3. And then looks like, let's find this area right here. 2 by 2 is going to be 4, divided by 2 is 2. So this is going to be a positive 2 area. And then this last section here, I'm going to use a different color just so you can differentiate that, is going to be 1 plus a half. So that's just going to be 1.5. Okay, so the overall area bounded by the curve of the x-axis is going to be 1 minus 3 plus 3.5, just adding the 2 plus 1.5 there. So let's see, that'd be 4.5 minus 3 would be 1.5 over 8. So we need to see which one is that equal to? Well, if I multiply both the numerator and the denominator by 2, 1.5 times 2 is 3, and 8 times 2 is 16. So our answer is B. Number 8, if y to the 4x squared, or y equals 4 to the x squared, what is y prime at 1? So first, we need to find the derivative of this function. We're going to have to use chain rule here, with our outside function being 4 to some power, and our inside function being x squared. So first, let's go over the derivative of an exponential function. Now, we know that the derivative of e to the x is e to the x, but really that's just a special case of exponential functions where the derivative ends up being the same thing as the original function. But in general, the derivative of something to the x power is going to be just that, but times the natural log of that base. And so the reason why you don't see that natural log of the base for when the base is Euler's number is because the natural log of Euler's number is just 1. So technically we do have a times natural log of e here, but it's just because that's 1 that you don't ever write it. So the derivative of 4 to some power would be 4 to that power, x squared, times the natural log of 4. Now, using the chain rule, we are going to have to multiply this by the derivative of the inside. And since the inside is x squared, the derivative of that is 2x. So if we want to try to evaluate this at 1, we're just going to plug in 1 everywhere where we see x. 1 squared is 1, and 4 to the first power is just 4. So you have 4 times the natural log of 4 times 2 times 1, which is 2. 2 times 4 is 8. So we get 8 times the natural log of 4. And our answer is E. Okay, number 9 says let f be a function defined as stated. So we've got an integral function where the upper limit is x. On which of the following intervals is the graph of y equals f of x concave? Concave down. I got a little typo there. So in order to be concave down, f double prime needs to be negative. And what that basically means is your graph is doing something like this. Okay, so we need to find the second derivative. So let's start with finding the first derivative, f prime, and we can use the fundamental theorem of calculus here, kind of the lesser used half of that fundamental theorem. Remember, part of the fundamental theorem just gives us the way how we evaluate a definite integral, but the other one tells us how to differentiate an integral with an upper bound that's variable. So we're going to plug in that x everywhere we see t, and then multiply by the derivative of x. Now, the derivative of x is just 1, so we're actually not going to see that differentiation happening. But just recall that if you've got a function, so let's say we want to differentiate any function where the lower bound is constant, the upper bound is in terms of x. I'm just going to write out this fundamental theorem here. You're going to get f of g of x. So we're going to plug in that upper bound, but then multiply by the derivative of that upper bound. Now, like I said, the upper bound here is just x. Derivative of x is just 1. So we're not actually going to see this part of it because we're just going to multiply by 1. But I do want to point out that that only happens if your upper bound is x. So 2 times x cubed minus 15 times x squared plus 36x. Normally we would say this whole thing times the derivative of that upper bound. But again, since the derivative of x is just 1, we're not going to write anything. So now we need to check the second derivative. So the second derivative is going to give us information about the concavity of the function. So we're just going to differentiate one more time. That'd be 6x squared minus 2 times 15 is going to be 30x plus 36. And we want to know when is that concave down? In other words, when is this less than 0? So I'm going to try to simplify this inequality by first dividing everything by 6. Let's make these numbers a little bit smaller. So I'm going to rewrite this as x squared minus 5x plus 6 less than 0. And so we need to find when is this less than 0. And so to do that, what I'm going to do is create a little sign chart here for f double prime. I'm going to put on the zeros here. I'm running out of space here, but I'll write it down here. This quadratic in factored form would be x, let's see, what would it be? Minus 6 times x plus 1. Okay, so we're going to have zeros at positive 6 and negative 1. Wait, is that right? Hold up. Minus 6. Nope. Let's try that again. That's going to be minus 2 and minus 3. All right, so that means the zeros are going to be at 2 and 3. All right, and since this is a parabola that opens up, I know that my parabola is going to do something like this, but you could also just pick values to plug in there. Like if I plug in 0, I can see I'm going to get a positive number. If I plug in 2.5, I'm going to get negative. If I plug in 4, I'm going to get positive. And so I'm looking for where f prime is, or f double prime is negative. So that's going to be in between 2 and 3. So our answer is D. That's kind of a tricky one. That's got the fundamental theorem and also the information about concavity. So you got to differentiate. You got to find the second derivative. You got to know what it means to be concave down. That's a pretty hard problem. That problem tests so many different pieces of calculus that we learned this year. So yeah, don't feel bad if you struggle with that one. Number 10 says, what is the equation of the line normal to the curve e to the 2x times natural log of x, where x equals 1? Okay, so first of all, what is a normal line? A normal line is the line perpendicular to the tangent line, specifically where x equals 1. So what we're actually going to do is find the slope of the curve when x equals 1, and then negate it and reciprocate it to get that perpendicular slope. Okay, so we're finding the equation of a line. So we need a point and we need a slope. So maybe we'll start with the tangent line, and then we'll move over to the normal line after that. So for the tangent line at x equals 1, we need a point and we need a slope. So the point is going to be at 1 comma, and then we need to find the y coordinate there. We'll come back to that. And then the slope is going to be, so this y value is going to be f of 1. So we're going to basically plug in 1 into the function. And then the slope is going to be the derivative at x equals 1. So let's start by just plugging in 1 so we get that point. So yeah, let's see here. E to the 2 times 1 times natural log of 1. Well, the natural log of 1, of course, is 0. So it doesn't really matter that we have e squared there. It's just going to be 1 comma 0. Now let's find the derivative of the function. So y prime, and we're going to have to use a little, we're going to have to use product rule and chain rule. Okay, so if this is my f and this is my g, I'm going to have f prime g plus fg prime. So the derivative of e to the 2x is e to the 2x times 2 times the natural log of x, that's my g, plus f, which is e to the 2x, times the derivative of g. And we know the derivative of natural log, of course, is 1 over x. Okay, so that's y prime. And so if we want to find y prime where x is 1, we're going to just plug in 1 here. So y prime at 1, we've got 2 times e to the, 2 times 1 is just 2. So 2e squared times natural log of 1. That's just going to be 0. So this whole thing is actually just going to be 0. Plus e squared times 1 over 1 is just 1. So yeah, it's just e squared is going to be our slope. Okay, so the tangent line would be y minus 0 equals e squared times x minus 1. Now that is the tangent line, not the normal line. So the normal line will have the same point. Okay, so the point is at 1 comma 0, but the slope is going to be the opposite reciprocal of the slope of the tangent line. So e squared, that's the same thing as e squared over 1. So the slope of the normal line would be negative 1 over e squared, or another way of saying that is negative e to the negative second power. So the equation of the normal line will be y minus 0 equals negative e to the negative second power times x minus 1. Now, the answer choices are not going to have the minus 0 there because anything minus 0 is just itself. So you can kind of ignore that part. But the rest of it, we're looking for this expression here. So negative e, I'm kind of just scanning back and forth. Negative e to the negative second power times x minus 1. Our answer is D. Whew. All right, that wraps it up. That is all. We saw some problems here on the second page that covered, a lot of what we have talked about this year in calculus. So hopefully, you feel a little bit better about some of these problems. It's okay if you felt like you kind of struggled with getting started on some of these, because with some of these, it's been quite a while since we've talked about these concepts. But I think with practice, as we move forward over the next couple of weeks with more practice of these kind of mixed AP problems, you're going to feel more and more confident with these, the more effort that you put into them. So anyway, thanks for watching. Y'all have a great night.